Thank you very much. Thank you, Emily and organizer, for the opportunity to invite me to speak. Let me actually let me also share the slides anyway. I forgot to post the slide link in case you need it.
Oh, sure. Yeah, that would be great.
But once you get a slide, don't just leave. That'll be embarrassing. So let me start from acknowledge my wonderful collaborator friend Yizong Yu for writing this overview together. And however, I would like to discourage you to read the archive V1 version because we do have the Juno version update several typos, and we may very soon update the V2, and you should read the V2 because we will add more descriptions and some clarifications. In addition, also acknowledge your wonderful colleagues, collaborators with Yuta, Hamada, Dachuan Lu, Mengzhen, and Zhenju work on other related works. Please interact with me and ask questions. The outline is that I will start with symmetry mass generation SMG kind of an overview in contrast with the conventional mass kind of mechanism, symmetry breaking. And then I will give you a concrete example in a 1+1D. Actually, there's someone has a microphone on. Maybe you should take. There's a 1+1D example was anomaly-free within the symmetry, but it's a chiral symmetry, a chiral fermion theory. I would like to give some concrete example for the symmetry mass generation on this model. And it has applications to solving a fermion doubling problem, Nielsen-Neumeier fermion doubling problem for the lattice chiral fermion chiral gauge theory regularization problem, and based on some earlier works and recent numerical simulation. And then I'll move on to say something about how the symmetry mass SMG type of understanding can help us to possibly have some new insights or new thoughts on solving strong CP problem. And lastly, I'll conclude with some more application, but I feel like the time will be really limited, so probably I will just say a few sentences. I won't have a time to say as much as a wonderful other new works, but we'll see. And those things are about Fermi surface, not just a Fermi point. There's many fermion modes around the Fermi surface, and there will be more complicated, more exotic type of SMG. And then also some possible application to flavor hierarchy problem. But this will not be the main part of my talk, probably just be some advertisement. Okay, so let me keep going. So conventionally, when we have a fermion, if we want to write down some mass, field theorists usually will start with writing down a Lagrangian and write down an explicit or spontaneous symmetry breaking mass term. And here, psi can be derived fermions, and there are some pairing like psi bar psi term. However, generally, we should pair possible minimum fermion like minimum representation of a spin space-time Lorentz group, like a vial or maybe Marana or Marana vial via Dirac or Marana masses. But in my talk, I will just be a bit sloppy on writing the mass, just say psi bar psi in general for this quadratic bilinear type of mass term. And we learned that if we just solve equation motion, we know how it behaves. And we also know that we can find out the dispersion relation. When we write some momentum k and energy, we'll find out that changing the momentum k, the energy dispersion goes like this. If it's a massless, then there's a cone, famously called Dirac point. Above there's a Dirac cone. And if there's a mass gap, then it will go dispersion like this. And then the mass above the zero energy point will be the mass. And however, we will comment very soon that maybe we should find other way to identify masses other than just solving equation motion in this quadratic or Gaussian type of theory. But it's probably better to look at the fermion correlation function when it's a short range, means exponentially decay for 2-point function, distance by x with exponential decay. Then the mass can be identified as the inverse of the correlation length. Any questions so far? Okay, so we should go a bit careful because fermion mass may really still be defined even we don't start with a free fermion fixed point or free fermion limit. Sometimes we may not be able to solve equation motion and with many fermion interact. And sometimes we may not know whether the quasi-particle or particle we start with may be a good description for under the interaction. However, if the fermion is a good operators, we can still define some two-point correlation function, and we can still probe what I just described earlier. The exponential decay will be signatures for the mass. Correlation length will be inverse of the mass. And if it's massless, then there is some power law decay, and we can read a scaling dimension like this. Any question? So let's even go further about possible other way to think about mass. If it's a many-body quantum system, we may just try to diagonalize a Hamiltonian, and there's some energy spectrum. If the system has translational symmetry, then momentum is a good quantum number, and we can label K, and try to find out the K and E, energy E versus K. So there will be some so-called energy band, and we can identify the minimum energy gap and specify the chemical potential, and we can say what's the energy gap. And this will be the notion of a rest mass. In some sense, this is more like the energy related to a mass, like E equal to mc squared, that type of mass. And we should also emphasize this kind of definition of energy gap should be applicable to general many-body quantum systems without even using a translational invariant or momentum K to label the E. Just generally many-body quantum system, you can diagonalize Hamiltonian and solve in the eigenenergy and find out the gap. However, if momentum indeed is a good quantum number and there's an energy band, then we can look at the inverse curvature of the fermion dispersion. In that case, you also say something about how curved this band is, and the larger the curvature, the smaller the the larger the curvature, the larger the mass, right? Yes, I actually, yeah. Anyway, so I hope this description is correct. I think it's correct. Yeah. So this will be more like a force is equal to F is equal to ma, that type of inertial mass. So the main message here is that the energy gap for this and the dispersion relation in general for many-body quantum system may not be related. However, for Lorentz invariant system, we know that actually these are related. But right now, we just be careful, try to specify they are different type of notional mass. And there's also a so-called bilinear mass. If the vacuum expectation value for bilinear fermion, again, non-zero VAF, then you can read actually so-called mean field mass term M. And for the Dirac fermion equation that we just write down, all the three cases actually will be the same, but we should be careful. They may not generally be the same. They may be equivalent. Okay, so if we want to define mass, actually mostly we'll follow on this the energy gap or the correlation length, the one we just showed earlier. Instead of thinking about this the mean field mass or thinking about this inertia with the energy dispersion. Any question? Okay. So, but however, for the mean field example, also the Dirac mass, this example, and with Lorentz invariant, Lorentz symmetry, all these mass are the same. Okay. And now we like to go to some constraint from the symmetry. Suppose we specify a symmetry of the fermions, where fermions sitting in some representation R of the symmetry G. We can ask whether we are allowed to write down some symmetric bilinear form to pair the fermion. If it's possible to write down a symmetry-preserving bilinear form, then we can say these are a trivial mass term. For example, if we want to demand just U1 vector symmetry for the Dirac fermion, you can write it down. So these are okay. However, if you want to demand both U1 vector and U1 actual, then there's a forbidden. You cannot obey both symmetry, U1V and U1A. And then next, you can ask, is it possible to break symmetry to give a gap? If that's possible, these are the conventional mechanism, and go back to many people study symmetry breaking, Nambu-Goldstone-Anderson-Higgs, symmetry is spontaneous broken SSB. However, if the G cannot be, if we want to demand G still preserve, then are there other way to give a gap for the system? So this is the main part of the talk. In particular, if the system is actually anomaly-free, then we want to in general, there shouldn't be any obstruction to give a gap. And we would like to go focus on this one. And this will be so-called SMG, symmetry mass generation. And in contrast, if the system has anomaly within G, then either there might be obstruction to get a symmetric gap phase. So sometimes you cannot even have a symmetric gap TQ of T at low energy and topological order to give a gap phase. And that's another obstruction. However, in some case, we may be able to give a gap phase, and then we will call topological mass generation for that. And in that case, there's anomalous TQ of T at low energy. So we'll focus on this one. Any questions so far? Okay. So let's just recap again. So in d-dimensional spacetime, we want to give a mass to or gap to massless fermions, and with fermion in some representation of G, R over G, and we want not any symmetry breaking within that G, and we want not generate any topological order with low energy TQ of T for that. And for anomaly-free system, in general, we should check based on modern understanding of a cobordism group. There's a free Hopkin notation TP in d+1 dimension, G symmetric T invertible TQ of T. The index within that classification must be 0 or vanish to be anomaly-free. So we want to check that. And then we also want to go beyond this bilinear form type of mass term. So we want to forbid any quadratic bilinear pairing of fermions such that their anti-symmetric product give any trivial representation. And the key question here is that how do we go beyond this quadratic fermion, quadratic type of bilinear fermion term? So we want to have interaction. Okay. So one famous example, go back to 2009 or 10 by Fitkowski and Kitaev, is the symmetry mass SMG for 0+1D. They are collections of Marana fermions with fermions operator written in Hermitian operator chi, and there are some Clifford algebra, the the anti-commutators for them. And if we demand time reversal symmetry and also fermion parity symmetry, time reversal is anti-unitary, which only flip I2 minus I in measurement I2 minus I, and does not change fermion in this Marana fermion basis. And fermion parity will flip the sign for the fermion. Demanded symmetry basically will forbid quadratic Marana mass term, because the Marana mass term contain imaginary I to make the whole operator to be Hermitian. And in that case, time reversal will forbid the quadratic Marana mass type term for any bilinear Marana. And one must go to a next order, which will be full Marana operators. And the case they show is that within appropriate choice of coefficient, you can find out actually several possibilities to write down such terms, but they write down particular one and preserve a larger spin 7 symmetry group. But the main point here is that the minimum number of Marana to preserve T and Z2T and Z2F is the n number of the Marana fermions, and you can check the index for this anomaly class is 0-8 is trivial. And no bilinear fermion expectation value actually will be there's no VAF actually for this bilinear this term for the ground state that once you write down a successful SMG interaction, you can check that actually once there's a unique ground state, the unique ground state does not have a mean field VAF for this. That means that you should not view this type of interaction term as a mean field while treating a given mass to the Marana fermion. And this part, this information is very important. It will be used later again. Just we want to really specify some SMG beyond mean field. And another thing is that in 0+1D, actually fermion, this four-fermion operator actually still irrelevant. In the sense, in 0+1 dimension, any number of fermion operator solving a quantum mechanical problem is actually solving a finite dimensional matrix and then diagonalize the eigenvalue for the Hamiltonian. And so this type of terms, any term will be relevant in the sense of RG. So, but in general, SMG does not really ask the interaction need to be a relevant term. And that will also become important even in 1+1D. We'll see even the irrelevant term can be dangerous, a dangerous irrelevant term, as the coupling stress become non-perturbatively strong, it can actually drive gapless phase to gap phase. So any question for this? Okay. So I hope this is familiar example. So we'll go to the main part of the talk. We'll give a focus on some 1+1D example to show how this SMG work. So we have, say, the kinetic principle about just say anomaly-free or cancellation within this symmetry, and that's kinematics. But to really derive the dynamics is more subtle question. One thing is that you need to first write down the interaction, and second, you want to show the dynamics really work. So from kinematic dynamics is really a non-trivial step, and we will do that. So we are not just write down interaction, we really check it gap the system. And we want to show there exists some interaction. And in the example later, as long as in 1+1D system within U1 symmetry and multiple U1 symmetry for chiral fermion or fermion theory in general, you can show the anomaly-free always give you a one-to-one or if and only if way to design gapping terms, and dynamically it should work and preserve the symmetry for SMG. And the condition will be equivalent. It's kind of like a dual picture. The condition can be mapped to each other, and these are based on audio work. Okay.
Can I ask a question?
Okay, go ahead, Minjin.
Yeah. So when you say that when there is no anomaly, then you can design maybe a irrelevant interaction to gap out the system. Do you allow to add additional degree of freedom, which is not in the original system?
Yes, in general, I should be able to. In the example I'm giving for 1+1, I don't have to. But in general, I think it's allowed. So as long as you add the new sectors, doesn't change the anomaly structure, which you may need to specify how they transform under symmetry G, but they are also anomaly-free. You should be able to also do that. So these are just try to energy sector and interact and reopen the gap. But in the precise example we give in 1+1D, we don't require that. We can just using the degree of freedom we do have from the original fermion theory to achieve that.
Okay, thanks.
But sometimes the description might have a rewriting, so you will see, although I may not write the degree of freedom out of some description, sometimes in other description you may see additional new particle or new you will see. Okay. For example, one example for the fermion theory, one of the stories is just multi-fermion interaction within the 1+1D model. But you will find that this model will also be equivalent written as fermion integral with additional scalar field, and that's not written in the original theory. But once you integrate those scalar field, you will bring back to the multi-fermion theory, interaction theory, and we'll be very specific about that. Thanks for the question. So this model is very simple, just two left moving Weyl fermions and two right moving Weyl fermions. Central charge each is left 1, 1, and right 1, 1. And they have a U1 symmetry written as 3450 for the two left and two right. And we also choose another U1 symmetry 0543. And as quickly you will see later as well, is that the symmetry is designed to be anomaly-free under the U1. And the other symmetry also anomaly-free. And that's just simply the fact that the one-loop diagram for the probe for either of the U1, the mutual and the self and the mix all are anomaly-free. So there are three conditions. One can quickly check that's true. And so this is just low energy field theory. And any question? So there are two independent U1 transform those four fermion, and they are chosen in a way they are chiral. So you cannot redefine any fermion in any way to make it vector theory. And also, because we have a two left and two right, so you can rotate both two left as U2 left, and then and also the U2 right rotate the two right-handed fermion. So there's a larger symmetry for sure, even for internal symmetry. But we are looking at the subgroup because we want to have an anomaly-free. Within the larger U2L and U2R, there's many mix and anomaly within them. If you just choose the cotton subgroup to the false, there's also many anomaly. The maximum anomaly-free subgroup will be U1 square anomaly-free. So this will become even clearer later, but I just state, I think there are many experts, so this might be too simple for you. Any question for this? Okay. By the way, each one your microphone is not muted. So
maybe try muting your iPad.
Oh, my iPad is muted for sure, I think. No worry. So next, so this model is actually intrinsically can be realized in 1 plus 1D, but for the construction, for the sake of a relate to invertible TQFT, it's actually good to view each layers as a boundary of 2 plus 1D invertible TQFT. And there's a realization of a level 1 Chern-Simons theory, and which is in condensed matter is known as integer quantum hole. Or Chern insulator with Chern number 1. I hope this is readable, level 1, sorry. Yeah, this is. And each layer has its own anomaly, and each chiral fermion certainly has its own gravitational anomaly. And however, the combined system are meant to be gravitational anomaly free, and also all the U1 mutual and self anomaly free. So this is the way put them as a boundary state of the 2 plus 1D bulk, the boundary state of 2 plus 1D bulk, and each layer of a bulk is non-trivial. But if you combine them together, they can become a trivial TQFT, invertible TQFT. In the sense, trivial in the sense it's a trivial vacuum, not even an SPT or any type of non-trivial basis. Okay, any question? And one thing to say is that people check Hall conductance, but that's just the anomaly-free condition within this linear response probe for this two-point function. These are just equivalent way to say the Hall conductance within either U1 and U1 prime is Hall conductance 0. Any question? And if we just maybe just want to be more explicit again, so the U1, U1 prime are the gauge anomaly-free and 0 Hall conductance, this red condition. They can be formulated more generally by this symmetric bilinear form using some canonical form for fermion system as the odd entry along the diagonal. And they are 1, 1, minus 1, minus 1. And you can see the 2-point functions, this anomaly-free, anomaly coefficient is exactly captured by this Hall conductance coefficient. And they are designed to be all the mutual and self anomaly, gauge anomaly free. Gauge in the sense here, U1 gauge is a gauge probe. So right now, regard U1 as a background, as a global symmetry with a background field, and these are the background gauge field. And similarly, there is also gravitational anomaly free because equal number of the lateral moving modes. Generally, there's a cobordism class, and these all are perturbative anomaly. And one can check within U1 square, this Z4 are exactly the full case we are checking. They are all free. But if you enlarge U1 to the false, there's a lot of mixed anomaly. So we don't demand to having more symmetry than they have to. Just consider the maximum they can be anomaly free U1 square for the abelian sector, abelian subgroup. Any question? Okay, great. So so we designed this again just to be anomaly free, but what's the correct interaction to drive? The asymmetry is the main thing. Another thing to say is that because the charge assignment is bizarre, so you don't have a way to write quadratic or bilinear term of any mass term to preserve the two symmetry, or even any one of the symmetry, you cannot. So you must aid interaction beyond the quadratic term. Okay. And this question, I think for people who may familiar with this, maybe feel like this is not a difficult question, but if you don't know, then you should try to write down interaction term. But I think for people who are trying to simulate chiral fermion, actually, it has been a struggle to write down such an interaction term and convince the lattice community in the past to say that this work. Although in the time when we are writing this in 2013, we are very convinced this already work. We kind of bother say why many people kind of strongly against this work, and this paper is still not yet formally published. I think this story is very complicated, and maybe we can talk privately. But anyway, so this interaction term is proposed long ago, but just thanks recently to our collaborator with Yi Zhuangyou's group and Zhen Meng here, they do the simulations, and we try to simulate a model proposed back many years ago, and we really are able to show the only when the interaction stress G here are choosing to be the same stress and go large above certain stress, then the original polynomial, this algebraic decay type of correlation functions will change behavior to this exponential decay behavior. So which means change gapless to gap phase. And one can also check any symmetric bilinear that has the VAF that breaks symmetry will not have a VAF, so that you can check this symmetric map phase. So this is evidence this indeed work. Even though we will show or convince the audience say there's some theoretical reason it work. So any question for this, the idea of the claim? So only when this interaction G, the stress is turned on to be some above some critical stress, will go to a gap phase. So in this diagram, there's three fixed point. This is the free one, and there's a gap one, and there's also the CFT critical phase. If you only do perturbative RG, there is no relevant deformation to drive the symmetric transition, but there's a symmetric irrelevant perturbations. But that irrelevant perturbation cannot be shown to go to SMG phase. However, when the stress is critical above a critical stress, then you will see that you can go to a SMG phase. So if you do a perturbative RG calculation around this fixed point, then the RG flow will go to this direction. So this will go to the free fixed point, and this one will go to SMG phase. So if you only do perturbation around this, you will never be convinced this highly irrelevant fermion, the 6 fermion interaction between flavor number 4, 1, 2, 3, 4, 4 fermion can gap this chiral fermion theory. Any question? Okay, so the reason this is important is that if we use this invertible TQFT picture to realize chiral fermion on one side, and there's another domain wall, so there should be some domain wall picture, and another domain wall on the other side. There's a fermion doubling between the chiral edge and mirror edge. If we implement the SMG on the mirror edge, we gap them, and because they are irrelevant, and only when the stress is above critical, they gap this. But because they are irrelevant, so small perturbations and just go to the other side, this interaction effect will be really, really tiny. You will not gap the chiral sector, so you only gap the mural, so you will leave the chiral sector remain. And for the finite width system, it will become just as good as the dimension of the system will just be as good as the chiral sector with some finite width, some kind of extra orbitals or extra degree of freedom with some finite leg. This will be just a regularized chiral fermion on its own dimension. That's the idea. So this is idea gapping the mirror fermion from the vector theory. I think that back to Ashton Presgill. And there's a domain wall fermion, mirror fermion construction by domain wall fermion lattice people by David Kaplan. And however, people wasn't really sure, for some reason, they are not sure how to argue that the gapping term really exists, and not even know whether anomaly-free is a sufficient condition. But for this system, and we believe in general, as long as you are sure what's anomaly, how to define anomaly, then kinematically, completely, then there should be a design principle to have a gapping term. Any question? So if we want to show that this dangerous irrelevant term really gap it, then one way to show is that actually you bosonize it. And this will be related to the chiral boson or Luttinger liquid at the edge of quantum Hall states. Since Holden in 1995 and later Kapusin-Salina and me and others, many people, also including I think Justin here, they are studying high central charge even more recently, I think the concept is similar. Basically, try to design a way to have a topological gap H of the Chern-Simons theory. In that case, you want to define a topological boundary condition, and you want to write down some terms. On the boundary, there is some cosine term you can add, and the phi will be multiplied. When you fermionize bosonize the theory, the psi will map to several compact boson. And in this case, it's ring full, so there's a full component of the phi, and they have a 2 pi periodicity. They have a K matrix specified earlier, and with some velocity matrix. And the condition we want to write down is basically write down such so-called L term, and such this L term has this so-called mutual annual conditions or Holden stability condition. But this condition can be interpreted as the line operators extend from the boundary to the bulk. So you can think this cosine term in the next slide will show as the boundary of some exponential ILA of some gauge field of the Chern-Simons free form of the bulk. And then we want to check whether this boundary condition is stable. It means that we can move those line operators around. If the partition function is gapped, then it shouldn't be affected by how you have the lines braid around each other in any non-trivial link configurations. So you boil down to check the partition function with any link configuration to be trivial statistics 1. If this is not bosonic, so up to some volume form, by the way, depends on you put on which partition function, for example, on 3 sphere and etc. It has some volume form, but the phase, complex phase must be 1. Then if it's 1, then it's stable. If it's not 1, then there's a fluctuation. So it's not. Then it will not be sufficient to argue that the H can be stable and gapped under the condition we are going to specify. Okay, I guess I say it, but I'm not sure whether you follow. Any question? And in the next few slides, we'll show even step by step why this is true. Okay, so this is the mutual statistical condition to argue there's a topological gap condition. Let me just recap what we have so far for the quantum number. So we have this two right moving biofermion with U1 3-fold-50 and 0-fold-53. And as we say, there's additional U1 you can specify, and you can easily map them by this K, and you will map to the other two U1. And they will span some lattice known as non-round lattice for people study compact boson and string theory, non-round lattice. I'll write it also later. And what's important here is that we add the interaction term, which is multi-fermion interaction term, and we bosonize the fermion term interaction term to a cosine term. And the coefficient for the fermion power is exactly this. And the coefficient for this L, integer L, quantized number is also read as this. And the main part here is to notice this L1, L2 is exactly the linear combination of the charge from the U1 third and U1 fourth. And if you are quick, you will see that the U1 first and U1 second actually is preserved by adding these two interaction terms. But U1 third and U1 fourth will be broken down to a discrete subgroup by adding this cosine two interaction term. And the structure is very compact in the sense that there's a one-to-one correspondence to write down the interaction term and to demand the anomaly-free symmetry. So they will pave the way to prove anomaly-free and gapping conditions will be equivalent. So there's a relation between kinematics to be anomaly-free and the dynamics of driving to a gap phase. Okay. So let's say the proof of gapping condition. I kind of sketched earlier, but we want to have fully gap and consistently achieved by condensing some not single boson, but some multi-bosons or multi-fermion terms. So these conditions is meant to achieve that because I was drawing the picture. If you have this boundary operators, vertex operators on 1 plus 1D, they can be extended to the line operator in 2 plus 1D bulk. And then you can try to check if that boundary condition specify a successful condensation, a stable, then any configuration that you try to braid them around, the partition function computed shouldn't depend on how the configuration was linked. So the minimum way to check is this invariant, right? And in general, if you see my previous paper, I check a lot of link invariant. So that's the kind of things we need to check if you want to define the consistent topological boundary condition. And in math, there's also define some Lagrangian subalgebra type of condition. But the physical picture now should become clear. We are specifying some differentiated, I think, boundary condition for how the A can end and how the phi will condense by driving the cosine term to be large. This cosine to be large coefficient, and you will go to a gap phase, and this will be consistent condition. So this will be a first way to argue this work. The second way is that if you try to do a mode expansion for this compact boson theory with 0 mode, winding mode, and Fourier mode, you can try to solve the large G expansion and then solve the energy eigenspectrum. You will see the zero mode, winding mode, this phi p, they don't commute, and with sufficient checkable conditions, they can give a gap if you input enough of this L, cosine L term. And however, if you only have the maximum amount of the gapping term that you add satisfy this condition, this will be good. It will show that there's a slight shift of the higher energy modes depends on 1/L system size. However, if you include additional interaction term, they are not compatible. The statistics are competing with each other such that this condition fails. For example, if you add too many interaction terms, then you will drive the spectrum to be unstable. In the sense, when you change the size of the system, actually the energy gap will increase dramatically, and there is also some weird behavior. It's largely due to the non-commuting condition implied. You try to condense two operators which are competing, non-commuting, right? So that's a problem. So that's also a way to say why the stability of gap is related to this commuting condition. And lastly is that if you try to find the basis for the rank 2-1K matrix, actually you can change such that you can find the basis. They become n decoupled copy of a Luttinger liquid, and each of them has a gapping cosine term, at least at low energy. And in that way, you can show that each sector is gapped, and that is known long ago, right? Even before side reference in this. So once they decouple, it's just a standard Luttinger liquid go to a gap phase. Okay, and the condition also, not just having the gap condition, we also need to design such that it's symmetry preserving, such that under the transformation of U1, this inner product was 0, so the cosine term will not break the symmetry. And these are really many works people study this. And if we just put everything together, the condition of the anomaly-free and gapping condition, and also symmetry preserving, they are basically mapped to each other. There's a one-to-one map between them. And if you put it together, I hope it's good. If you put together and then just follow what I was saying earlier about this 2U1 symmetry neutral set of anomaly-free and the gapping condition, they are mapped under the other broken U1 third and U1 fourth. You will see that this is exactly how do you map the charge Q to the L vector that has gap. And the computing of the statistics partition function to be trivial phase EI 2 pi 0 1 is actually mapped to anomaly-free, even though the physics is very different. So some people are confused, say, oh, these are the same thing. No, they are not exactly the same. They are mapped to each other by some relation. And they are spend the half of the dimension of the neuron lattice for this integer charge lattices. Any question?
But then the conditions are equivalent. So you said it's 1 to
yes,
1.
It's 1 to 1. Yeah. So the condition will be equivalent under the map, but under the map they are the same. But I would still say the condition when you write it down, they are different. Just before we specify how do you map Q to L, actually these are two different conditions, right? And but the thing is that once you know these are anomaly-free, and once you demand you want to have L preserve the symmetry, interaction preserve symmetry, then you can find out the existence of L once this is anomaly-free. and vice versa. If you have a way to gap them, and if you demand the gapping term preserves symmetry, then you will find this will be an anomaly-free system. It's almost like tautology, but I don't feel like it's exactly the same, because we are proving anomaly-free condition is gapping condition. Because anomaly-free condition in general you might know. Nowadays you might just compute the covolution group, but to design the gapping term we may not know. I can give you a very complicated system and to be anomaly-free, but you may not know how to deform such a system to gap phase, where all the paths of deformation has no symmetry breaking, right? So yeah. So I hope you still appreciate this is still a non-trivial statement, even though this is really a benign, naive description. Okay.
For the topological gapping condition, it's only defined. You only have to be obeyed to be 0 mod 1, not.
Yes.
Exactly.
Yeah, this is the subtle part we are trying to avoid. Yeah, very good. So you're trying to say this can be possible some multiple integer, is that right?
Yeah.
So here, indeed, I think in general it might be true, but here we are demanding a stronger version of that. I would say I think Michael Lavin might have some proof between the condition of that one, this one, and the one that you mentioned. We are using the stricter one. Yeah, I'll avoid to comment further.
I see.
Question. For statistics, indeed, you don't need to have a 2 pi 0, but here we demand 2 pi coming into 2 pi and 0. Sorry. Okay. Yeah, so the picture just really go back to draw that if we have a chiral fermion which is anomaly-free, these are like sector gapless, and this span half of dimension of non-wrong lattice. In this case, it's 4 dimension, 4 U1 and 4 two left, two right fermions, and they are anomaly-free, and you can design them as light gapless. And on the other hand, we can know how to gap them, and the condition map to each other by this map. And in this case, gapping them does not necessarily imply they are anything different from the original starting sector. But the good thing is that if you view them as two sides of a domain wall, fermions with chiral and mural sector, then we can regard the other sector as a dark sector. They are gapped, while the chiral sector are light and gapless. And this picture works for the anomaly-free 3450 model in 1+1. But I think the picture here should be pretty general. For example, if we take a standard model within a 3+1D model with SU3, SU2, U1, if we know it's anomaly-free within some number of biofermions, then there's also implication that you can design such a neural sectors and gap them. And they are massive, they have a mass, but they are dark in the sense they are really highly gapped above the spectrum by SMG gap, but with no like additional. You don't have to introduce Higgs to give them a mass, but they are just gapped by interaction. In general, you might just design some interaction among them and gap them. And that's an implication of the toy model we studied for 1+1D, but it could have some deeper implication for other things. So there's a light sectors and there's a dark sectors. Any question for this?
Yes. On this page, I have a question. Does there have to be a parametric separation in the energy scales between the gapping interaction and the gap in the actual the bulk phase, Chen-Simons? Because the fermions are gapped in the bulk, which is why you have edge modes. But you also want to gap the fermions on the edge. Does there have to be a separation between those two scales?
Very good question. So as we start to say the bulk we design is invertible TQFT, which means the insulator. We say the Chen insulator or the quantum hole insulator. That means the edge, the two sides is original is gapless, and there's a gap, energy gap, if you draw the spectrum. And right now, we are trying to gap them in a way. Yeah, sorry, don't do anything. Yeah. something. Yeah. So we are trying to gap one edge, and you are asking the energy scale. Let me. Actually, I don't know whether each one you have any comment about the energy scale. I think can be as large as the bulk gap if you want to, but certainly we can have a energy that is several order of a smaller gap for the other mirror edge. So I think the condition really.
There was a critical strength of the so there's a critical strength of the coupling.
Right, you need to go be above some critical stress. But I can say one thing maybe that will make you happy is that if you start with
bulk energy scale is much larger than the boundary. Even you go beyond the critical interaction, I think the interaction on the boundary can be small compared to bulk. So bulk never enter the picture, I think.
All right.
Yeah, bulk does not enter the picture. Yeah, enter the discussion directly. We always maintain this gap, but I think one point I want to make is that in a lot of discussion about gapping the theory, one thing is that we are not relying on perturbative theory, which means if I write down the theory with kinetic terms, the free part, or just the the chiral fermion part, and plus the interaction part, it's natural to have both terms to gap achieve SMG. Actually, the coefficient of these two need to be order 1. It's kind of a naturality condition people like. In the sense, usually we may want to start with a kinematic term to be large, while we do perturbation theory around small interaction, small g. Or the other way, if we want to turn on very strong interaction and then do a perturbation along the weak kinetic interaction. So we are considered two limit. But to achieve SMG, at least at near the critical point to achieve the SMG to make it happen, actually, this ratio of this, say the G, will need to be order 1. It's kind of naturality condition. That's a comment I was trying to give earlier. But but it's true the bulk gap is kind of independent from much of discussion. It can be just a gap much larger than other energy scale.
And if that G, instead of being O1, was O something much larger, then the answer would be different and the bulk energy gap would come into play. But it's the fact that are you saying the fact that the critical interaction strength is O1 is what means that the edge gapping does not interfere with the topological insulation in the bulk? So explain.
I think then the bulk gap should be much larger than O1, than the interaction.
Okay, yeah. Okay, thank you. I have another question about 2 slides back.
Okay.
Maybe 1 slide back, actually. No, maybe 2 slides before this one. Yeah. So the expression En equals. So yes. I don't understand this argument. This is a continuum analysis, right? You have the chiral bosons in the continuum.
Yes.
There's no lattice here. So how is this? Yeah, what exactly is this showing? Is it showing that how could it be showing that a gap opens up in the spectrum? Because you need to be on a lattice to see this happening. You need to be on a lattice to have a critical coupling strength. Otherwise, in the continuum, the critical coupling would be infinite, because in the continuum, we're basically in perturbation theory around the free Fermi fixed point. Yeah. So this. I'm not sure what you say lattice. This one doesn't rely on lattice. These are just compare chiral boson and mode expansion, and assume that the cosine term has large coefficient, such that you assume that there is already a VAF developed for the large cosine term coefficient, give a VAF to this L phi term. So EI phi have a VAF. Then you try to see whether this can maintain an energy gap for all the energy eigenmode for this mode.
And certainly this may not be true, right? So that's the thing I'm trying to check. I say that these are something naive analysis, you can see whether these are stable in a sense. And the end of the result say, suppose the terms you aid are compatible under this condition, then the energy gap computation makes sense. However, if you aid a different type of cosine term and such that they don't have this condition obey, they are competing, and you will see this competing effect. The G and G prime are different type of cosine term, let's say, and G prime are interfere such that violate this condition, then you will see there is some weird behavior. And I think that suggests that you cannot even start with doing the calculations.
I see. So it's not showing that a gap opens up the symmetry action. It's saying that some other interactions would not work. But right, so it's used to suggest what interactions to look for.
Yeah, these are more like a stability of the energy gap analysis. I'm not sure. Did I answer your question?
I think so. Yeah, I see what you're saying. Yeah, thank you.
This is more like just kind of a possible consistent check when the gap, when you want to say whether it's gapped, but certainly this term, if this term occur, which means that condition is violated, that means that this analysis actually does not follow it. You should not work for the case when there is a competing. That's kind of
because there's a 1 over n, which suggests the calculation is broken down.
Yes, that's the point.
All
yeah.
right.
You can check that. It's kind of non-trivial check. Yeah, but anyway, there are many other arguments I try to give. So, oh, sorry, let me just make sure where I'm at. Yes, let me quickly. So let me summarize. We have explained this one, and so there's a light and dark sector. We'll go back to this in the third part of my talk. And here, just quickly say that even though we write down this particular type of gapping term, they looks highly complicated, but they are actually the minimum possible scaling dimension operator you can write down. Around the free fixed point, it has dimension 5, while the marginal operator is dimension 2 in the energy scaling. These are dimension 5. But you can actually not necessarily write down this term. Any linear combination of this operator will work as long as they span the 2-dimensional neuron lattices. They will work. And the other dual direction that is going outside this plane, another the direction going outside the plane, there will not be. There will actually be the symmetry that corresponds to the symmetry that is preserved. And while this 2-dimensional this plane will correspond to the symmetry that is broken, and that's also corresponding to the gapping terms. Okay, these are related to the picture I was trying to say about this the relation between these two. I think people will get it if you deep. Yeah. Okay, and that's it. So there's a bosonization map between them. I think it's kind of repeating, and these are the dimension 5 operator, and that's it. So one thing is that even though these are non-renormalizable irrelevant interaction term, but we really rely on to use these operators if we want to start from a free fermion fixed point to drive interaction. We really need to access those type of terms. And then this will become something important for deformation class or quantum field theory later. And yeah, so I guess it's almost end of this part. I say that if we do numerics, as we did with Zhenmeng, is that it shows that the scaling dimension of the multi-fermion operator is going from dimension 5 at this free fermion fixed point, and gradually it will go down to scaling dimension 2, which is marginal and only near the critical stress, which is something around 6. And that's it. So there is some renormalization due to Luttinger parameter and reduce the scaling dimension. So make the multi-fermion operator gradually become important and more important, and then eventually drive the gapless theory to a gap phase. And it's a non-perturbative effect. Any question? Okay, so 5 to 2 become marginal and then change to the SMG phase after this. Okay, so that's it. And we also argue that this is the familiar BKT transition, but I won't go to detail. And yeah, I kind of just say that it's marginal relevant flow only when we go above the GC, but it's irrelevant when you start from this. And yeah, I think I can just skip this. There's related to Yunqian's question is that actually we can rewrite this multi-fermion theory by introduce bosons, and such that bosons have some Feynman rule specified by this tree-level interaction between fermion with bosons, and there are some particular power for this boson. There are two bosons. Let me call this Yukawa scalar, phi1 and phi2, and then there are some dynamical variable, and we should regard as they should be summing over in the path angle as a dynamical field and with all the possible configuration, and they generate the interaction terms. If you integrate all those phi1, phi2, as you will see, you will generate this multi-fermion terms. So this will be another way to rewrite multi-fermion term with some interaction like this. And now we can use this to argue whether we can gap the system. So on one side, so let me just also pack everything in the table, is that this everything is what we just say earlier, the multi-fermion interaction and all the charges. And there's also certain combination make the theory to be having a vector symmetry. This will be important in the third part, the strong CP part, but right now just omit this. And we can rewrite these two multi-fermion interaction terms as some disorder Yukawa scalar interaction with fermions. Okay, so this is a table. And with that, we can say, suppose we try to make phi1, phi2 condense in the sense they have a vat. If that's possible, then we will generate bilinear mass term. And because they are just some quadratic bilinear fermion with phi have a vat, right? However, in 1+1D, the continuous symmetry associated with this cannot be spontaneous broken, where the phi1, phi2 indeed carry the U1 and U2 symmetry, U1 and U1 prime, or U1 first and U1 second symmetry, in order to make the interaction to be symmetric. Then the phi1, phi2 condense will break symmetry, but we know the continuous symmetry cannot be spontaneously broken. So at best, actually, boson can end up with some algebraic instead of just usual long range order with some finite expectation value for this two-point correlation function at a large distance. These are the usual long range. In the algebraic case, is polynomial or so-called algebraic decay, but it will decay just as power law, right? So not violating this Coleman-Morgan theorem. And if that algebraic long range order is developed, then the fermion will still see such a correlation length for the boson is still pretty large, almost infinitely large, right? And so fermion's correlation length is still much smaller than this phi, and you will see as if the phi can still have some kind of VAF, at least at some range where fermion correlation, where fermion can see. So in a sense, fermion indeed see the boson can give a mass. So the fermions can still see as if phi has some kind of a so-called quasi-long-range order condensation and give a mass to the fermion. So this is basically some way, at least in 1+1D, you can argue that this quasi-long-range algebraic long-range order effectively still can give some kind of mass to the fermion. And then even though there's no really expectation value, but let me just recap again. We first argue that there's a algebraic long-range order, and then in the range of this this power law decay because of large correlation lengths, the fermion still see this effectively still see effect as psi as if psi obtains some mass from this boson long-range order, quasi-long-range order. But we want to go to the case such that phi become fluctuating and dynamical. And in that case, we want to argue that there is still no symmetry breaking, and the phi does not have any VAF. And this can still successfully drive us to the fully symmetry gap phase, and with so-called disordered mass. And so these are like two-step argument, saying that using the algebraic long-range order to say you can see fermion get a mass, and boson has algebraic long-range order. And the second step is that gradually the boson become disorder, and the mass can still be maintained, hopefully at least at some range. And these are related to some earlier ideas one had in higher dimension, although it's probably harder to argue in a higher dimension, but in 1+1D, at least based on this two-step argument, we can say that. And lastly, because we make phi dynamical, once we integrate phi, we can generate the multi-fermion interaction term. So this will be another way to go to the gap phase, just to argue the gap phase for this fermion theory. So any question?
I have a question. Do both bosons have even charges and all U1s?
Yes, I think so.
All right, so you could replace the bosons with charges of, well, with bosons of half the charge, and then everywhere you had a boson, replace it with boson squared, and that would also seem to work. Would this system, would there be any differences with this system? Just half the charges of the bosons.
Maybe I'm not sure. What might be the concern? So there could be other description as well. I guess we find one.
I'm just wondering. You could half the charges of the bosons and use boson squared where you previously had one boson. I'm just wondering, is there any difference between these systems?
Sorry, you mean here we require two scalars, and are you saying you just change the charge here, or you're changing also the number of boson?
No, change the charge from to -2, -1, -1, -2.
But there's a particular, I guess one need to check whether this term still right in the way.
Can't you just write phi1 to the power 4, then phi1 squared? Just put a square on every boson.
I think there's no difference as long as when you integrate our boson, you recover the original 6 fermion interaction. But if you use phi1, if you further fractionalize boson, you may want to concern there are more channels that is opened due to this fractionalization of the boson. You may want to check that they don't lead to other unwanted interaction. But if that's fine, then as long as the fermion interaction is the same, it should be the same thing. Yeah.
Okay. I was wondering if there might be some extra discrete symmetries in one of the cases that's not there in the other. Maybe that could be spontaneously broken. Or yeah. I don't know. Okay.
You are saying there may be discrete symmetry associated with this fractionalized boson, right? Or it's almost like gauge freedom if you try to fractionalize the original boson into fractional charge, right? So yeah, that could be a possibility.
I think
just consider the simplest case where we don't further fractionalize the boson.
One thing I can comment, if you change, you also demand the expectation value for that will be also higher power to be 0. So that means you are demanding further non-mean field behavior if the power of the boson is also higher.
Would I have to demand the power of the boson is higher? If I do fractionalize it, then I could just demand the same condition, f of phi and phi squared is 0. That still not be good enough.
Well, I think the whole whatever in front of the fermion bilinear, that one, the VAF must be 0 in order to not have any symmetry breaking.
Right.
Also, really go beyond mean field. So that condition, we don't want to keep that. So any operator O, if I call SMG and with any fermion psi or zeta, I want to demand O SMG mean field to be 0. So that's a condition. You can certainly change the theory, but that's a condition I want to keep. Maybe there are many ways to rewrite this theory for sure. Yeah. Anyway, we can discuss later. I think it's not quite crucial. I guess kind of limited. So let me know how much time do I have time to mention what I want to say? Or
yeah, I think we should wrap up within the next like 10 minutes. So
okay, great. So let me quickly say something about this symmetric mass, this type of way. How do you possibly help to understand CP problem, strong CP problem? Okay, and I'll conclude very soon. So just recall, previously we have this table with several two right moving biofermions, and with U1 symmetries, and eventually the U1 need to be gauged in order to have a U1 gauge theory, and with the so-called theta term. In 1+1D abelian gauge theory can have this F, field stress F, which is effectively the electric field. F01 is the electric field. And then this U1 dynamical U1 gauge theory, this theta term will be a term that violates both the P and CT, and for generic theta, except the 0 and pi, right? So this is known. Okay, and by the way, I should mention that in some case we may start with U1 as a background. It's a global symmetry and coupled to background field, and then we gauge the U1. So the argument will be careful, but when I state it, maybe the detail, sometimes I will just be quick. So I hope you can follow. So we may use the gauge principle, either use global U1 or gauge the U1. Okay, so if any of fermions is massless, then actually you can do a chiral rotations, transformations, such that the theta actually can be rotate to 0. As long as this chiral symmetry that do the transformation for the fermion has the mixed anomaly with the U1 of that field stress U1. Okay, so that fact should be clear to people who know the mixed anomaly. Once you do the chiral transformation, you will rotate the theta. So here we will choose field stress F for the first and second U1 because that's the mutual anomaly-free U1, and we should be able to gauge them. And then we'll rotate the theta by any chiral transformation that has mixed anomaly with this first or second U1. As long as that fermion is massless, then when you do that chiral transformation, it will not affect any terms. And this will be related to so-called massless fermion solution or massless quark solution for the CP problem, strong CP problem. In 1+1D, these are actually just P problem or CP problem. The property of the CPT is slightly different in 1+1, 3+1. So let me just generally call P problem. P problem is always true for 1+1 and 3+1D. So then, yeah, so that's. And now if we give a fermion some mass, conventionally like standard model with a Higgs valve, so we will do that. In that case, we want to pair some of the left fermion and right fermion in some way, and here I write it down in this part. So they are bilinear fermion mass, fermion mass termed by this Yukawa Higgs, and if the phi has a valve, you will break U1 first and U1 second, but they are designed to break down spontaneously caused by this algebraic quasi-Lagrange kind of modification. So to this U1 vector, and so this will be a U1 vector symmetry remain still preserved even if you add the Yukawa Higgs term and even if you have the Higgs mechanism coming. And in that case, the theta cannot be arbitrarily rotate to 0 in the sense without messing up the mass term, because the mass term will also have some complex phase on the top, just in exponential, some factor exponential I complex phase on the mass term. And this is known that the real physical parameters should be a theta bar, written as the linear combination of a theta plus angular part of a determinant of a mass matrix. There will be a physical invariant term. And the question there is that once we are in the case that with some Higgs phase similar to standard model and with some mass generated from the mean field mass due to the Higgs valve, theta cannot be arbitrarily rotated. In a sense, it will also affect the mass this complex phase. Then the theta bar cannot be rotated to, generally cannot be 0. cannot be rotated to 0. Is there a natural way we can still set the theta bar to be 0 or small? So that's a way to ask whether this is possible. Okay, so this is a problem for this 1 plus 1D system. And let me say a few words how this is possible in the new view of thinking about symmetric mass generation. So as we say, the U1 we are choosing that we are going to have this field stress F, theta F, the instant long term is the vector U1, and which are the linear combination of U1 first and U1 second. And under any of the quark, let's say left or right, or some of the quark, any left or right via fermion, there's a mixed anomaly between the U1 vector and this U1 vector and U1 left, right. So this mixed anomaly means that you can rotate theta, but you will also rotate the mass. And the way they are rotated are written in these 3 lines equations. And similarly, you can choose the remain the other U1, U1 third, U1 fourth. They also has a mixed anomaly between U1 first and U1 second. So that's mixed anomaly between the third and fourth with U1V. So this expression just say that there's some compensation between how you rotate theta and m. And the question is that whether the physical invariant part of the theta bar from this face can be rotated away. And in the conventional way of thinking, the massless quark solution just say if any of the mass m is 0, and which give determinant m also 0, this quantity certainly can be rotated to 0. And this solution, I think, date back to 't Hooft. In the case of if m has some VAF and up to the description in 1 plus 1D, we really require quasi-long range, not really long range. But we can still try to give some VAF at least locally, and then there's some dynamical fluctuation around it. And this can be viewed as some kind of a action or pseudo-Goldstone type of solutions for the problem for generally for solving that theta to be small, in a sense using the dynamical theta to relax the condition. So I'm drawing either thinking about this as a mean field mass or thinking about the theta as because theta and the mass is actually related. However, the main part of the talk, I think from the second part, you see that the multi-fermion interaction also has a description from so-called the disorder or the Yukawa scalar, dynamical Yukawa scalar interaction. And that way of thinking say that the mass may be generated, but without a mean field mass. So this is more like a target space, for example, for the disorder scalar or the mass, the disorder mass term for the m. So you can think this as the bosons written in this SMG or SMG, and then now they don't have a particular VAF. If they have a VAF, you will go orient in certain direction. Right now it's like disoriented. It's also the disorder phase. And the thing is that if that disorder phase is possible to maintain the operator OSMG is 0, and that's exactly what I demand the non-mean field SMG, and side by side this mean field value is 0 due to the linear response. These the two conditions are related. Then the full mean field mass determinant m for the mean field part is also 0. And the interpretation of the theta bar written as the theta plus angular power determinant mass m can still be set to 0, as long as some of the fermions or some set of fermions get the mass from SMG, and some of the fermions does not have any mean field mass. Okay, so is this part clear? So as long as some of the fermion has this mass m equal to 0, just some of them, well, perhaps it can still gain mass from the SMG, symmetric mass generation. So the mass interpretation might be different. Then in that case, we can still do chiral rotations on the fermion to rotate the theta away, because the full determinant of this mass matrix mean field is still 0. This is more or less like if we want to ask what's the value of theta bar, the question of the strong CP is more like whether the theta bar is oriented in certain direction, like 0, small, or pi, or pi over 2. then the clock need to be oriented in a certain way. But if the system has some of the disorder, some of the fermion fully get mass from disorder, then we are hard to compare the theta bar, because it's hard to compare the shift of the theta bar theta when the clock is shift. When the clock is shifted by a constant change, but it's already gained a disorder oriented field in the clock, then you still cannot tell what exactly is the direction of the theta bar. Any question for this? Just to clarify. And yeah, and another way to see this is that if this solution of mean field mass is solution, then if there's a way to go through a phase transition, or quantum phase transition or deformation from this phase to the other phase, the validity of one solution also implies there's a possible validity of another solution as a different realization. So this might be one realization on one side, and this will be another realization. So the two solutions are related by some quantum phase transition as a general way of deformation. In between, there could be some quantum critical point or quantum phase transition in between. But in the larger side of phase diagram, you can deform such a solution to the other side. For example, like people study duality or abelian duality from the particle degree of freedom to a vortex degree of freedom. Similar picture work. If you don't get a picture, please ask me. And if you do, let me just quickly. So similarly, in the problem in 3 parts 1D, the question there is the theta bar for the strong CP measured by experiment. Say these are 10 to the minus 10, smaller than 10 to the minus 10, and the mass metrics from the Yukawa-Higgs for the quark U type and D type are written as this form, mu and md, and the physical invariant theta bar is a theta 3. Physical invariant theta bar is this theta 3 bar, and content is SU3 theta 3 plus angular part of the determinant of the mass matrix. And the SU3 theta 3 has indeed mixed anomaly with U1L and U1R, so you can do a chiral rotation again. But again, there's only a physical invariant theta bar. This is not changed under this chiral rotation. So you cannot solve the rotated theta bar to 0 unless there's additional condition, right? And the similar condition here is, again, say that a Tohu solution is massless U quark. If the U quark is 0 and determined mass is 0, and you can rotate the U quark, define the chiral transformation, and then redefine the fermions on a new basis, and such that rotation will not affect this massless quark mass matrix, but you can rotate the theta away. So this is massless quark solution. And in 3 plus 1D, we do have the long range order mass, and we do have this condensate, and the fluctuation around the theta give action. So this will be a Pesquin solution. Imagine tuning the theta to be from the order phase to a disorder phase. And imagine the condition the SMG gap can still maintain. Then we also further demand there's the SMG operator or SMG pairing with any fermion bilinear has no mean field depth. Then as long as you can generate some mass for the fermions or for the quarks that observe partly in the experiment, then we can possibly replace or introduce new sector of the fermions with some SMG gapped fermions. Then we can use the symmetrics to do a redefinition of the theta 3 bar and rotate it to be 0. So this is the idea. And it turns out there's two different ways to deal with this. One is without introduce mirror fermion sectors. The other is with introduce mirror fermion sector, and which go back to the second part of my talk. And so far, let me just say these are proposal. This could be a theoretical solution, but there could be many experimental constraints. So we don't know where experimentally there's already bound to say some of the solution may not work. Just like Tohu solution for massless quark, this solution is already ruled out by lattice data in the experiment. But I don't know enough to say whether these are experimentally consistent, but let me just propose all this possibility. And the first one is we just propose the possibility the first one without mirror fermion sector is that if some of the chiral fermion actually may have not the mass from the Higgs-induced mean field mass by SMG mass, then it's possible. So this will be SMG version of massless U-quark solution. Although we don't know whether U-quark really can gain the mass from SMG, it's not evidently known whether U-quark has zero or non-zero Yukawa coupling because we don't really directly observe U-quark. And they are bound in the proton, neutron, and mesons. So the way to do that requires a lot of detailed simulation from lattice data, and there's a lot of assumptions. So this part is unclear, but that's just a possible proposal. But there could be some challenging from the U-quark asymptotic-free behavior at high energy. The second possibility is that possible you introduce a new generation of anomaly-free chiral fermion, maybe fourth generation. But there's also difficulties because they need to couple to standard model forces, and they may have some channel to see them, but maybe we haven't seen them. But just based on try to relate SMG-induced non-mean field mass to give a solution for strong CP, this is still theoretical plausible. Okay. And the solution part 2 is related to this gapping mirror sector. In this case, actually, we have a less constraint because we just propose a mirror sector and we don't have much probe yet. And the construction here, again, relate to Nielsen-Ninomiya fermion doubling of domain of fermion with chiral mirror sectors. And the second one is the parity reflection symmetry will map the chiral fermion to mirror fermion. At least at the UV when you write down a theory, and I will show that. But the important part is that this does not require doubling of the gauge group. In a sense, some of the previous solution by many people here in the past, these people, they propose so-called parity solution or Nielsen-Bar solution. In some case, they need to double the gauge group. And here, for the sake of understanding the fermion doubling, they actually couple to the same global symmetry. So there's not necessary to double the gauge group. And this parity reflection symmetry I will show in the next slide is that it will be spontaneous broken by SMG at the intermediate energy and the Higgs at the IR in the one at the chiral, this SMG on the mirror sector and Higgs in the chiral sector. So there's also a realization of why the parity is violated in the standard model. You can some way to kind of explain that in the sense of just like many model in the past in the granular theory, like left right model, and these are also have some left chiral and right mirror sectors. But yeah, so as you say, SMG gap mirror by Higgs mechanism gap the standard model chiral fermion. And physically we enlarge the CR3 bar to include the mirror sector CR3 bar prime, and then include the mass from the UD quarks, Yukawa Higgs matrix, and also the SMG. But if the SMG mass has no mean field mass, this actually has a 0. And that's a part you can try to do the chiral rotation to redefine the theta bar. Okay, so this is the idea. And the detailed construction, and I'll end my talk in 2 slides, I think, is that this is the mirror fermion type of solution, is that you have a chiral sectors and the mirror sectors. They are fermion doubling. They couple to the same symmetry, extend to the finite width bulk. And the parity maps left to right on the same sector. Reflection map chiral to mirror sector. So parity reflection will map chiral fermion lab to the mirror fermion right, R prime. And then that Z2PR symmetry is meant to be preserved at some high energy, possibly gauged at high energy. And then it will impose a condition such that the both CR3 from the chiral fermion sector and CR3 prime from the mirror sector, they are mapped to each other, and they can demand the overall theta for the FOGF for the full theory. When they couple to the same field, actually they are vanished. So this is the UV way of already having some solution. But now we need to know whether IR will generate some effects. So there's many discussion in the past. There could be IR correction to the parity or Nielsen-Bar solution, because the idea is kind of similar. There's some UV preserve parity and or preserve generalized parity and solving the strong CP, but there could be some IR effect which might make this CP violating theta bar still show up at IR. In their solution, these are higher loop correction, and they find that this effect is very small. And that corrections even the effect such that both the chiral sector and mural sector are gapped by Higgs, which is marginal and relevant interaction. And remember, we are really driving the SMG by the irrelevant deformation. And in that case, we believe that this effect will be smaller, even smaller than the previous parity Nielsen-Bohr solution. So if their solution works, I suppose replace the mural Higgs to the SMG Higgs will be even a better way to avoid any CP violating IR. And that's it. So the SMG give a large gap to the mural fermion, and there are some different energy scale above SMG scale, much above SMG scale, but below the Planck scale, there's a parity reflection symmetry imposed such that the UV preserve this CP and theta bar is effectively totally zero. And then at some low energy scale, one need to argue there is no further CP breaking, but I suppose it will be a better way, even better than their solution in the past. Okay, so yeah, let me conclude. Thanks for the attention. The final message I want to give is that in this talk we try to start with some free fermion, chiral fermion theory, massless, and drive the interaction gradually become strong, go to the SMG phase. And these are non-perturbative interaction to give this effect. However, in general, we may believe that this will work not just for simple 1+1D model. For example, if we consider 3+1D standard model of unified theory with a gauge group like SU5 or spin 10 and with certain number of fermion 15, 16 in proper representation, preserve some symmetry or keep some. For example, 15-valve fermion, you actually need to break. You may not keep B-L, but for 16-valve fermion, you can keep B-L, and there are some additional constraints. But in any case, as long as you check this series anomaly-free, there should be a path to go from a gapless fermion theory to a gap fermion theory. Okay, so this will be a symmetric mesh generation in high dimension, and people are discussing that. And there's also topological mass generation in the sense that even the theory has anomaly, then we can still try to replace or try to go from a gapless theory to a gap phase. For example, if we have an SM or SU5 with 15-valve fermion, and even with some discrete B-mass cell symmetry, the right-hand neutrinos on one side of massless fermion theory can go through some quantum critical point and go to a exotic T2D or CFT. Okay, and the conclusion is that in this talk, we have say the fermion actually can get the mass without bilinear condensation and without any symmetry breaking within the anomaly-free symmetry. And there's a kinematic conditions we know is anomaly-free, but we try to use anomaly-free to derive some derivation on gapping conditions and write down explicit interaction. Also, we verify some 1+1D example numerically to show this successfully can gap the fermion. If we apply that to a mural fermion sector, it also has implication on regularization of chiral fermion in 1+1D. And there's explicit proof in 1+1D. But in general dimension, high dimension, we may not know yet, but there are some arguments. And there are some features about critical theory with emergent parton, emergent boson of fermion, and emergent gauge field. These are related to deconfined quantum criticality. And there is some additional CFT and with some property of scaling dimension. I don't have time to discuss. I also don't have time to discuss fermion green function, but it has been shown by Yizhuang and other people, the determinant of the green function in this omega frequency and momentum, there is some green function 0, especially at the omega frequency go to 0. So these are the features to say SMG phase may distinct from the conventional Higgs or mean field mass type of gap phase. And there are applications other than what I just said about the lattice and also classification of interacting SPD phases. I mentioned the possible way to look at the strong CPS, the disorder phase, instead of older kind of Page-Quinn solution. And then I don't have time, but we recently tried to apply smooth confinement similar to Raza-Martin's SMG model to the flavor hierarchy of Sinda model with collaborator Utah Hamada. And potentially, there is also some reason why we did try to give a symmetry, a Fermi surface reconstruction without symmetry breaking for the Fermi surface, such that it may have application to slow gap phase in high TC superconductor. So thank you for your attention. And sorry for going a bit over. Thank you.
All right, let's all thank Juven for the very nice talk. Are there more questions for Juven?
Please feel free.
All right, well, there were a number of questions during the course of the talk, which was nice. I think for now, let's thank Juven again and stop the recording, and then we'll stay on for a bit if people have additional questions. So thanks again, Juven.
Thank you, Emily.